So let's read this problem. It says that Paul is standing in the schoolyard. The figure shows the distance from various classroom doors lined up along the same wall. So in this problem, this is your wall right here. And this is where Paul is. Now, what you've learned in class is that the distance between a line and a point is the distance from the point to the perpendicular to the line. So what we're saying is that we have to identify which of these lines, this one, that one, that one, or that one, is perpendicular in order to get his distance. So this is a fairly simple problem because all you have to do is understand that this is your point for Paul. This is your perpendicular because it's at a right angle. So the distance is 246 feet from the wall. Okay, so for this problem, it says that Mason is standing on the seashore, and he believes that if he makes a wish and throws a seashell back into the ocean, his wish will come true. Mason is standing at the origin of a coordinate plane. So the origin, as you know, is the point 0, 0. So I've marked that in red. And I've put the scale as 2, 4, 6, etc. And you can see the scale above as well. So here's where he's standing. So here's where Mason is. And the shoreline is represented by the line 1.5x plus 13. So 13 is about here. And then I go down 3 over 2 or up 3 over 2. Remember that each one is 2. So 1, 2, 3, 1, 2. So that's your rise over run. So I've already graphed that line for you as well. So it says that each unit represents 1 meter. So in this case, it represents 2. So let's keep that in mind, although that doesn't really matter right now. And then it says, how far does Mason need to be able to throw the seashell to throw one into the ocean? So what we're looking for is the perpendicular distance between where Paul is. So this is where Paul is, not Paul, Mason. I don't know why I keep calling him Paul. So Mason is at the origin, and this is the shoreline. So I've drawn this right here, which is your perpendicular, okay? So the first thing that I need to know is that the slope of the line is 3 over 2, and that's because 1.5 equals 3 over 2. So the slope of the perpendicular is negative 2/3. And we also know that that line passes through the origin. So the equation of the line is y equals negative 2/3 x plus b. But since y and x are 0 for that particular point, then 0 equals 0 plus b, and b equals 0. So the line is y equals negative 2/3 x. Now that I have both of them, I'm going to go ahead and solve the system. So I've actually made a little bit more space for us so that I can do some work here. And so what I'm going to do is I'm going to draw, write out my system. So I have y equals 3/2 x plus 13, and I have y equals negative 2/3 x. So now I have to find the point of intersection before I can find distance. So what I'm about to do is I'm going to multiply by the fraction so that I get a non-fraction system. So I get 2y equals 3x plus 26. And I also get that 3y equals negative 2x. And so now I'm going to multiply the first system by 2 and the second system by 3. So I get 4y equals 6x plus 52. And I get 9y equals negative 6x. When I add these two equations, I get that 13y is equal to 52. So y equals 4. And then I can go back to, let's say, this equation right here. So 3 times 4 is equal to negative 2x. And so 12 equals negative 2x. And x equals negative 6. So now I'm going to go ahead and find the distance between the point negative 6, 4 and the origin, because that's where Mason is, which is 0, 0. So I'm going to reset oh, I can't reset, I apologize. So I'm going to just do it really small over here. So I'm going to say that the distance is equal to the square root of -6 squared, because if I subtract 0, I still get 0, plus 4 squared. So that's the distance is equal to 36 plus 16, so it's the square root of 52. And then 52, I'm going to do it over here on the side. Divided by 2 is 2 and a 6. 2 is 13, so it's 2 square root of 13. And that would be my final answer for the distance that he would have to throw that. And you can check on your calculator to get a better approximation.